So just picking up from the last video, we ended on example 9. Now we're going to go to example 10, where we have Wellspring, which is 14 miles north and 3 miles east of Chester. And then we have another town, Hilford, which is 8 miles east and 5 miles north. I forgot to include that in the writing here, but it is north of Chester. We want to find the area of the land. I have some typos here. This should be land formed between these 3 towns. So there we should have north inserted. So we've actually got all the information here. We can set this up as a triangle where we've got a vertex at Wellspring, which we'll call 3, since that's east-west would be left-right, 3, 14. We've got Hilford, which would be 8, 5, and then we'll call Chester, since it's the direction to each of the other 2 towns, we'll just call Chester 0, 0. So if we set up the matrix, we're going to have 3, 14, 1, 8, 5, 1, and 0, 0, 1. So let's start by finding the determinant, and remember to do that we take those first 2 columns and we rewrite them to the right. And then we're finding the diagonal. So we've got 3, 5, and 1 in a diagonal, 14, 1, and 0, 1, 8, and 0. We're going to have 14, 8, and 1, 3, 1, 0, and 1, 5, 0. So when I looked at finding the determinant, we go 3 times 5 times 1, which is 15. You can go 14 times 1 times 0, that's 0, and 1 times 8 times 0, which is also 0. So if we add those, we're going to get 15. And then we can go 0 times 5 times 1, which is 0. 0 times 1 times 3, which is 0. And then 1 times 8 times 14, which is 112. So our determinant is going to be 15 minus 112, which is going to give us negative 97. And to find the area, we take half of negative 97. Which is going to give us the area of 48. And now, here's the thing. We are dealing with an area, so we don't really need to make this negative 97. We'll call it positive 97. So our area is going to be 48.5 miles squared. So then the identity matrix, which we denote as I with a subscript n, is a square matrix that if we multiply by another matrix, it's just going to give us that same matrix back. So we say if A is an n by n matrix, a square matrix, and I is also a square matrix, n by n, then if we take A times the identity matrix, we get A back. And if we take the identity times A, we get A back. Now an identity matrix contains only ones along the main diagonal. Main diagonal meaning the first element to the very last element. And zeros for the remaining elements. And I have drawn here an example of a 2 by 2 identity and a 3 by 3 identity. Now we also are going to talk about inverse matrices. We say two n by n matrices are inverses of each other if and only if matrix B exists such that if we go A times B, we get the identity matrix. Or if we go B times A, we get the identity matrix. And then if matrix A has an inverse, we denote that as A with a little power of -1. Then we can say if we take A and we multiply it by its inverse, we're going to get the identity. And if we were to take the inverse and multiply it by A, we get the identity. So in our next set of examples, which we're starting over at 1, we are going to determine whether the pair of matrices are inverses. So remember, to multiply 2 by 2 matrices, we are going to just take the first column of the first matrix and multiply it by the first row of the second, and then we add those elements. So A times B is going to be -1 times 5. And I need to correct myself. It's actually taking the first row times the first column. So -1 times 5, that's -5. And then we add 2 times 3, which is 6. And then for the first row second element, we're going to take the first row of A, -1, and multiply it by the second column of B. So we go -1 times 2, get -2, and then we go 2 times 1, and we get 2. Now we just repeat the process, but this time we take second row, first column. So we go 3 times 5, which we get 15, and we add -5 times 3, which is -15. And now we go second row, second column. 3 times 2 is 6. -5 times 1 is going to give us plus -5. So now we can make the addition. -5 plus 6 is 1. -2 plus 2 is 0. 15 plus -15 is 0, and 6 plus 5 is 1. So are these inverses? The answer is yes. Alright, let's check on example 2 if G times H. If G and H are inverses, so G times H, we're going to get -6 times -5/3 is going to give us 10. And then if we go -3 times 3, we get -9. -6 times 3, -6 times -1 is 6, minus -3 times 2 is -6. And then in our next row, we're going to have -15 plus 15 and -9 plus 10. So if we combine everything, we're going to get 1, 0, 0, 1, which means, yes, H and G are inverses of each other. Let's check out example 3. So we've got R and S. So we're going to go R times S to see if they're inverses. And I think as far as determining if these are inverses, this will be the last one. We'll skip the next example if you're using your note packet. So we're going to have -8 times -6 is 48, plus 3 times 16 is also 48. Then we go -8 times 2, so -16 minus 15. Then we go 4 times negative 6, negative 24, minus 32. And we go 8 plus 10. Which means we're going to have the matrix 96, negative 31, negative 56, 18, which this is not an identity matrix, which means R and S are not inverses of each other. So now the question is, do all matrices have an inverse? Well, no, they don't. But what we can say is if we were to find the determinant and it equals 0, then we don't have an inverse. So then if we want to just find an inverse, if we know the matrix, so say we have a 2 by 2 matrix and we've got, we'll just call it A. To find the inverse of that matrix, we take 1 over the determinant of A and we multiply it by, we switch the A and the D terms, and then we take the opposite of the C and the B terms. And we say the determinant can't be 0. Otherwise, the inverse does not exist. So let's look at how, of the remaining examples, if you're using your note packet, we're just going to look at the first 3. And I think that should be plenty. So example 5. We want to find the determinant of this matrix. So first, not the determinant, the inverse. But we do need to find the determinant first. So the determinant of this matrix, we're just going to call it A for now. We go 4 times 3 is 12 minus B times C. Negative 6 times negative 1 is 6. So our determinant is 6. So our inverse matrix is going to be 1/6 times our original matrix. In fact, before we say our original matrix, we switch the A and the D terms. So we switch 3 and 4. And then we take the opposite of the B and the C terms. So we've got 3, 1, 6, 4. Now we multiply everything by a sixth. 1/6 times 3 is 1/2. So our first term, our first element, is 1/2. 1/6 times 1 is 1/6. 1/6 times 6 is 1. And 1/6 times 4 would be 4/6, which if we simplify that, we get 2/3. So our inverse matrix is 1/2, 1/6, 1, and 2/3. Let's look at example 6. So first we're going to find the determinant. We go 8 times negative 1, negative 8, minus 2 times negative 4, so negative 8 plus 8. That's 0. In this case, if the determinant is 0, we have no inverse. So I said we're going to just check out the first 3. Let's do one more. Example 7. So we're going to find first the determinant. We go negative 2 times negative 5, that's 10. Minus negative 6 times negative 6, so 10 minus 36, that's negative 16. So to find the inverse, we're going to take 1 over, correction I need to make on that determinant, it's not negative 16, it's negative 26. Which means when we're multiplying for our inverse matrix, we're going to take negative 1/26 times negative 5, 6, 6, 2. which means we're going to have in our first element negative 5 over 26, and then we're going to have negative 6 over 26 can simplify. They're both divisible by 2, so we're going to have negative 3/13, negative 3/13, and then if we go 2 times negative 126, we're going to end up with 1 over 13. So our inverse is this matrix that we just calculated. And I think we can leave the remaining examples blank in our note sheet, which wraps up our lesson on determinants, identities, and inverse matrices.